Hello and welcome back. Again, my name's Jeff George, professional engineer. I'm an initial license instructor at ANO Unit 2, former licensed operator at Palo Verde Nuclear Generating Station. In my professional experience, I think as operators we may have lost a step or two with fundamentals. So I wanted to take a few short lessons on exactly what you need to know as an operator for these. Kind of try to cut out the background and just get to the nitty-gritty. To that end, I wanted to do a recap of the six-factor formula. And how we can manipulate this to control the reactor. We'll get into the concepts. Number one is going to be the moderator to fuel ratio. And number two, the concept of overmoderated, undermoderated, and what we do to control the reactor under each of those conditions. So with that brief intro, I'll go ahead and start right now. The six-factor formula, which I think every nuke has learned in some way, shape, or form. There's various ways to remember it, but K effective. Remember, K effective is going to be equal to 1.0. That means critical, and that's going to equal every little French person loves the French Navy. I learned it a different way when I was in Naval Nuclear Power School. You may have learned it this way, and anyway, that's how I remember it now. So I'm forced to remember it now. But what are these things? This guy right here, every, this is the fast fission factor. And that's going to be equal to number of fast neutrons from all sources and the number of fast neutrons coming from only thermal neutrons. So what does this mean, all sources? So in a reactor we have fissile and fissionable materials. We have some materials like U-238 that can that can fast fission. In other words, fission from a nuclear fast neutron, high energy level neutron. We also have U-235, which catches and fissions from a thermalized neutron. Then we have plutonium. Some of them catch a fast neutron, some of them catch a thermal neutron. There's four of them, 239 through 241, 242, sorry. And that is all the sources of fission that get added to the reactor, right? So this is going to be an add, right? These only thermal neutrons, well, that's going to be basically U-235 fissions. Right? So this number is going to be greater than 1. It's going to be approximately 1.3. As the core ages, it moves. It's pretty, I'm sorry, 1.03. Let's scratch that out. 0.1. So a net add, but a little bit of an add, the fast neutrons. So this guy, it does change over core life, but you're not God, so you can't really change how much U-238 and how much plutonium-241's in the core. So there's really nothing we as operators can do about the fast fission factor, but it is there and it adds reactivity. So let's just kind of be able to explain that, and why we're going to ignore it. All right. So what's next? Little French people. This is going to be the fast non-leakage probability. All right, the fast non-leakage probability. What are the chances that a fast neutron that comes from fission will not leak out of the core? So it's going to be pretty low. Well, it's going to be pretty high that it won't leak out of the core. The core is gigantic, right? So L sub F is going to equal to number of fast neutrons that start to slow, that are born. Divide that by number of fast neutrons from all sources. And this is typically going to be about 96%, or 0.96, 0.96. So that means 4% of the fast neutrons that are born are going to escape the core. That's not very many. And we actually read power on our X-core nuclear instruments from that 4% of neutrons escaping the core. And that's why you can't go inside the bioshield at 100% power, because it's spraying out fast neutrons. Now, it's not that many compared to the whole, but still significant. Anyway, it is a net loss. So the thing is, again, you're not God. You can't control how many fast neutrons are going to get shot out of the core, right? So there's really nothing we can do about it. And it's so close to 1 that doesn't really help us control anything. Right? And of course, if the moderator is more dense, less fast neutrons can leak out of the core. But the core is so gigantic, this number is going to be negligible. All right, so we're going to go ahead and just kind of skip over that quickly. All right, the next one is every little French person, right, the P. That's going to be defined as the resonance escape probability. Resonance escape probability. The probability that a fast neutron that is slowing down will escape resonance. All right. Well, what's resonance, right? All the material in the core can catch a fast neutron if it is at the right energy level. So fast neutrons are in the mega electron volt energy level, and they're slowing down. So do you guys remember this graph? Boy, what's that thing, man? That's an average microscopic cross-section for absorption, right? And this was neutron energy. And fast is going to be over here, right? and not easy to catch a fast neutron, but it starts slowing down into the intermediate range. Now all the materials are going to be a little different, but they're all going to look like this, right? They're going to spikes, usually right here in the intermediate range. And then get a little easier to catch when they're in the slow or thermal range. And that's going to be this region right here. So fast neutrons get shot out of a fission and they start hitting stuff. All right, we want them to hit the moderator, because if they hit the moderator, even though neutrons are teeny tiny, a water molecule is relatively small, and it puts a lot of energy into the water molecule. That water molecule then heats up, and that's how we make electricity ultimately. But if the fast neutron starts bouncing around inside the fuel, it's likely to come upon maybe a plutonium atom that loves to eat neutrons at this energy level. And actually, the highest average microscopic cross-section that I've ever heard of for this intermediate range resonance capture, which is what that would be called, is about 7,000 barns, right? So remember, boron, its affinity or its average microscopic cross-section for absorption is around 3,800 barns. If the fast neutrons take too long to slow down, they will go farther, and it will take longer, more time in the intermediate range, and more likely to get resonance capture. Now that's not just plutonium. That was uranium, cobalt 60, iron 59. They can all catch neutrons, and this is our probability that they won't. So hopefully more fast neutrons won't get resonance capture than will. And in fact, this is going to be around 0.75 or 3/4. So 1/4 of all the fast neutrons should get caught up in some kind of resonance capture. And P, the resonance escape probability, is going to have a formula, right? And that's going to be the number of fast neutrons that become thermal they make it to thermal, made their parents so proud, and that's going to be compared to the number of fast that start to slow down. Excuse me. The number of fast neutrons that start, which is going to be all of them, right? It's net loss. Remember, a more dense, a more dense moderator makes fast neutrons slow quicker. And this is going to be an important part of what we control as reactor operators. I'll get into that in a minute. Next in the 6-factor formula was loves the, or the thermal non-leakage probability. And that's a probability that a thermal neutron won't leak out of the core. Now they have really low energy levels, and the core is so gigantic, this number is typically around 0.98. So about 2% of the thermal neutrons that are created, all the FASTs that make it to thermal, about 98% of those stay in the core, and about 2% leak out. This number's pretty much negligible. Plus, you can't do anything with it anyway because you're not God. Again, God made the reactor, not you. So we'll just move on from the thermal non-leakage probability. Now let's talk about F. What was F? Well, F's defined as thermal utilization factor. And I dare you to try to find 5 nukes who can tell you what F stands for. Well, they could probably all tell you what F stands for, but it won't be the thermal utilization factor, I can tell you that much. That is the number of thermal neutrons that are absorbed in the fuel, the ones who made it, who went and did what they were supposed to do, to the number of thermal neutrons absorbed in the core. What does the core mean? Well, the core is going to be the fuel. Of course, it's going to be the rods. It's going to be the clad. It's going to be the iron, the cobalt, stuff that makes the shiny pipe shiny, all that stuff. They're going to go get absorbed in it. But also stuff that gets sucked up into soluble boron. So I think we can all see we can control F, right? We can manipulate this number as operators. And in fact, P and F are the two that we will manipulate. I'll get to that in a second, all right? And remember, 5 boron 10 plus 0 neutron 1. And that'll give us 5 boron 11. Right, so it sucks up a neutron and kills reactivity, right? Because it takes away the thermal neutrons that could possibly cause fission. So you would think, over core life, there's less fuel, so there's going to be less thermal neutrons, but we're making plutonium-239. So actually, F has a slight rise over core life. It's not going to be much. I mean, this is going to have a reading of around 0.95. So 95% of the thermal neutrons get utilized. They get sent to fuel. If we pull rods out, they're more likely to go to fuel. If we lower boron concentration in the reactor coolant system, they're more likely to go in. And what we're doing there is we're manipulating the moderator to fuel ratio, which we'll get into in 1 second. So that was F, thermal utilization factor. All right, so there's one more. It loves the French Navy. fancy N. That is the reproduction factor. All right, reproduction factor. And that's going to be the fast neutrons from thermal fissions. Remember, fast coming from the thermal fissions. In other words, a thermal neutron met with the U-235 and made a fission. And that number is going to be divided by the number of thermal neutrons absorbed in the fuel. Not all thermal neutrons that go into the fuel result in fissions. Isn't that sad? This number is typically going to be about 1.45-ish, but there's really nothing you can do about it as an operator. You're not God. You can't make U-235 fission just because it found a thermal neutron. Okay? So we're going to go ahead, just call that negligible. Now remember what we say, K effective equal to fast fission factor, every little French, the fast non-leakage probability, person, the resonance escape probability, loves the, that's the thermal non-leakage probability, French, that was the, I never can remember, see, I already forgot, thermal utilization factor, and then Navy, the reproduction factor. Now I think we've already talked about how we can't do anything about this guy, can't do anything about this guy, or this guy, but man, the P and the F, so K effective is going to be approximately equal to people Frenching, or French people, or however you want to talk about it. That's what we control, people Frenching. Okay. The resonance escape probability and the thermal utilization factor. All right, now let's talk about something called the moderator to fuel ratio. The moderator, that's how you usually see it drawn. I'm lazy, sometimes I'll say moderator fuel, so bear with me if I do that. Changes in temperature of the monitor, change the moderator, and you can change that as the operator. But you can't really change the fuel. The fuel changes itself over the core life, but in the instantaneous or in the now, you'll be manipulating the moderator to manipulate core power. Okay. Moderator to fuel. First you got to remember this graph right here. This is going to be density, and density is pounds of mass per cubic foot. All right. And then temperature, you might recall, is degrees Fahrenheit. So remember, this graph looks like this. Okay. Now we're up here at 550, and we want to go to 551, and we're going to have a density change of this much. Okay. But if you're down here at 200 to 201, still the same distance, that's going to result in a density change that is significantly smaller. So we run our reactors up here at 550 to 620 degrees Fahrenheit. So a small change in temperature will result in a large density change. That's a good concept to know before we get into this. So the change in density from 550 to 551, much, much greater than the change in density from 200 to 2001. Right. So remember the resonance escape probability. That was P. And remember, the resonance escape probability is the probability that the fast neutron that is slowing down won't get resonance captured. So the quicker it slows down or loses energy, the less likely it is. All right, the thing that's going to slow these guys down is more moderator. More moderator, right? More moderator is going to slow down quicker, and the resonance escape probability is going to rise. All right. Now, as temperature of the moderator goes down, therefore density goes up. Okay. Therefore, what happens? The density is going to go up, so the fast neutrons are going to slow down quicker. P is going to follow. P is going to follow. Wait, that's not right. No, P is going to rise. Sorry, not P is going to follow. P is going to follow density, not temperature. I want you thinking in temperature. P is the opposite. An easy way to remember that is, I'll show you in a second. All right, so we change the moderator, we change P, we change resonance escape probability. And we can draw a little graph of that. P. And what would the bottom of this graph be? Well, this would be moderator to fuel. Okay, so as the moderator to fuel coefficient rises, the ratio rises. What is that telling us? There's more moderator or there's less fuel. Okay. So if we go over here to 1.0, meaning 100% of the neutrons that start to slow down escape resonance. That's going to be more likely at a denser moderator. So more moderator. These guys are going to. This graph looks like this. Okay. So as a moderator goes up, P will get closer to 1. So the moderator going up will actually result in temperature going down. Temperature goes down, we'll get a more dense moderator. So on this graph, temperature rising goes this way. That's a weird concept to think of. But the rising temperature will go this way. So moderator temperature going this way will result in P getting lower and lower. Cold moderator, hot moderator. And that changes the density, changes the moderator to fuel ratio. your mind, didn't it? The effect of moderator temperature change is more drastic. Oops, sorry. It's more drastic over here, right? See how P is changing? And that's because of that density change at higher temperatures up here. That's what causes that to be more pronounced. So if you go from cold to lukewarm, well, P says, it's no big deal. But if you go from cold to super hot, like 600 degrees, P's really going to change on you. See that? And that's because of density changing at higher rates with temperature when you're hot. Okay, so there's P. That's how we manipulate P. We manipulate that moderator, the fuel coefficient. So let's talk about F. F, the thermal utilization factor. Thermal utilization factor. And that's thermals absorbed in fuel divided by thermals absorbed in core. So this is an easy one because remember core means rods, boron, that means iron, cobalt, clad, that's everything, okay? Number absorbed in fuel or number, well that's easy to know, man. We can manipulate the rods and we can manipulate the boron. But we're actually manipulating the moderator to fuel. I can't spell, sorry. Oklahoma public education failed me again. We manipulate this moderator to fuel coefficient, not necessarily the fuel, although it's changing over core life. We can manipulate this moderator. We've already seen that with the P resonance escape probability. So, where was I? As temperature of the moderator goes up, okay, we all know that density is going to go down. And that means more spread out, less dense moderator. So there's less moderator atoms to absorb energy and less thermal neutrons. So less mod atoms. So less thermal neutrons likely to get to fuel. So as temperature rises, F follows. And since F is the first letter in the word follow, you know that F and P are opposites. And F follows temperature, so that you know that the resonance escape probability will go down as temperature rises. So if we go here and we graph, and this was a 1.0, right? That's perfect for us. That means at 1.0, the thermal neutrons absorbed in the fuel and the thermal neutrons absorbed in the core are the exact same number, which they probably never will be. There's one. F is going to follow temperature, and it's going to go down and look like that. So, wait, that was P. Oh, doggone it. Let's see if I can do that. F is going to go here like that. And now, this is the moderator to fuel ratio. So density. Now the moderator fuel ratio will rise this direction And density that means density gets bigger in that direction. And that means temperature of the moderator gets big in that direction. So as temperature rises, well, F rises, it follows. Okay. Ultimately getting to 1 in some imaginary place. So over here, this is hot. And over here, this is cold. All right. Not a big changes if we're still, excuse me, if we're still cold, but bigger changes if we're hot. And that is because of the density changes. This graph right here, very important concept to know, okay? The more drastic density changes at higher temperatures cause F to be move more active. Okay? And F follows temperature. P does not follow temperature. It does the opposite. There's two P's and opposite, if you want to remember it that way. All right, so what does all this mean? We want to control KF, right? Okay. So K effective, if you do a graph of it, it's going to look like this. KEFF, the 6-factor formula, right? And 1.0, as we all know, is going to mean critical. So let's go down here. That's the critical line. The K effective is going to look a little bit like this. All right, there's K effective. There's going to be this K effective max. And it's going to come at a certain moderator to fuel ratio. If you were on the right side of this graph, if you have loaded up your fuel and put in your moderator at a certain temperature that puts you on the right side of this graph, you are over moderated. Well, heck, man, how do they deal with that? If you load your fuel up and you put your moderator at a certain level, meaning you have a certain boron concentration, you have a certain temperature that leads you to be on the left side of the K effective max, you are under moderated. All right, so what does that mean? So if you are on the over moderated side, let's go say red for fire. Sure, red for fire. You're over here. All right, so that's your K effective. So you got to borate to get down here. All right, but that's your K effective currently. All right. If you raise temperature, so over mod, temperature rises. Where's that on this graph? So again, remember, moderator fuel ratio is going to get bigger this way. Density is going to get bigger this way, but temperature of the moderator is going to get bigger this way. So if we raise moderator temperature, we're going to go to here. Right? Temperature of the moderator goes up, and that means K effective goes up, and that means supercritical, and that means reactor power goes up, and that means temperature of the fuel goes up, and that means temperature of the moderator goes up, and that means K effective goes up. Power, fuel, moderator, and on and on and on and on. So heck, man, that's hard to control. How do we control that? We do control that. I have done that personally. So we do that by lowering power. How do we lower power? Well, we're going to lower K effective, and the only way to do that when you're over moderated is to raise the moderator to fuel coefficient. So how do we get more moderator in the core? How do we do that? Well, let's take some boron out. If we take some boron out, some water goes in. That'll do it. So we dilute to lower power in overmod. That's weird, huh? If you're a licensed operator, you'll think, man, that's dilute and raise power. It raises TAB. You've seen it 100 times. Now, say your reactor engineer did this. He set you up with a core that's under-moderated, which is what most of them do because they're a lot easier to handle. And that's because in an under-moderated core, all right, so temperature rises. And what would make that temperature go up? Maybe close down a little bit on the turbine control valves. That's the easiest way to do it. Temperature rises. All right, so temperature goes up, and I think we remember temperature gets bigger here, so we're hotter, colder, this direction, okay? So temperature goes up. What happens then? Well, K effective goes down. K effective goes down. Power goes up. Power goes down, sorry. Power of the reactor goes down. Temperature of the moderator goes down because temperature of the fuel went down. So it kind of controls itself. So temperature went up, and now temperature's gone down. More control. You don't have maybe runaway freight train down here with the daisy chain of power rising. Okay. And how do we manipulate the neutron or moderator to fuel ratio here? Well, you get more moderator in the core, you raise K effective. So to raise K effective, say power got low, you want more moderator to fuel. Okay. How do you do that? Well, you dilute. You lower boron concentration in the RCS, and that lowers K effective. So as opposed to here where you dilute to lower power. I'm sorry, that raises K effective. Doggone it. So on the under moderated, you lower the boron and that raises K effective. As opposed to when you dilute here, you lower K effective in the over moderated thing. I hope this helped explain something, a nice little refresher. Again, let me know if you have any comments, any constructive criticism. I really enjoyed doing this. Thanks for listening. Bye.